Hello everyone, welcome to IIT and Gate classes. So today we are going to start one of the most important and the most basic topic of computer science, that is TOC. Okay. First of all, let me tell you about its weightage. This subject constitute around 6 to 10 marks in your entire Gate CSC paper. So see the weightage. It has a huge weightage and hence I am calling it one of the most important topic for computer science. Okay, so very first question which will come to our mind is what exactly is TOC? TOC is theory of computation. Theory of computation. Okay, and the next basic question which will come to our mind is what exactly is a computation? Okay, so computation is whatever a computer do. Okay, whatever a computer do is nothing but a computation. So what exactly computer do? We all already know this thing. See, we supply some input to computer and it will do some processing and give us some output. So this processing is nothing but your computation. So how exactly we can define computation? Computation is nothing but a process of converting input to some output. Okay, we are converting input to output and this is nothing but computation. So we can give lots and lots of examples of computation. For example, we give input to computer as small case letters and output will be uppercase letters. So the simplest example of computation can be converting a lowercase letters to uppercase letters. Next example can be, say we supply some numbers, say 5, 10, 9, 3, and the output is 3, 5, 9, 10. Okay, so that is sorting of numbers. This is also an example of computation and so on. So simply see, roughly I have already told you whatever a computer do is nothing but a computation. So whatever you think, see, you are making program of lots and lots of problems now. So each and everything whatever computer is doing is nothing but a computation. Okay? Or and another simplest example can be you are giving some numbers as input, say 2 and 3. You are giving two numbers and output is 5. That is nothing but 2 plus 3 is equal to 5. So computer is doing addition operation. This is also an example of computation. You can call this as calculation also. Right? This is nothing but calculating the sum of two numbers, that is 2 and 3. Right? We are calculating the sum of numbers. Okay, so this is also an example of computation. So calculation is also a type of computation. Okay, so remember the fact that every calculation is computation, but every computation is not a calculation. Okay, so we are doing beyond calculation. We are doing lots and lots of things with the help of computer. So roughly, I have already said you. I have repeated many times also. Whatever computer is doing, whatever you think, okay, whatever computer is doing, that is nothing but computation itself. Okay, I hope I have justified the statement and I have already cleared all the concept related to your that basic term computation. Okay, so next is what is this theory? What is this theory? So theory here means how machine perform these computations. How actually machine perform this computation. How machine perform computation. Okay, this is the basic meaning of theory here. That is, we will deal with the theoretical aspects related to the computation itself. Okay, so this is the basic meaning of theory here. Okay, so let me move to next slide and we will study some more deeper meanings of this subject. Okay, so let me take the next slide. I hope by now you have already noted down all these things. These are very basic things. Okay, so in this subject, next question will be what are the things which we are going to study in this subject? Okay, so we are going to study two things in this subject. Okay, so the very first is how machine perform computation. How machine perform computation. Okay, This is the first and the very basic thing which we are going to study. And the second is, given a machine and a task, whether this machine, okay, let me give you a rough idea, okay, and then I will write it down. I will write this statement. Given a machine and a task, whether this machine is capable of doing this task or not. That is the second question. And in one word, I can say this statement is nothing but computational capability of machine. Computational capability of machine. Okay? Computational capability of machine. So let me say it again. Computational capability of machine means, given a machine and a task, whether this machine is capable of doing this task or not. That is the basic meaning of computational capability of machine. I have used the word machine lots and lots of time till now, and you all must be wondering what are the types of machines which we are going to study in this subject. We are going to study about abstract machines. Abstract means imaginary machines. Imaginary machines, that is, which do not exist in real world. We will study some theoretical machines, you can say like this also. Okay, so examples of these machines are, say, finite automata, that is FA, PDA, push down automata, LBA, linear bounded automata, Turing machines, and so on. Okay, we will study lots and lots of machines in this subject. And computational capability means whether FA can do addition or not, whether PDA can do multiplication or not, whether Turing machine can do division operation or not, whether LBA can do power operation or not, and so on. Okay, so these are some examples of computational capability. So whether FA can do addition or not. So this is a task, na? Addition is a task, and FA is a machine. So FA is a machine. Let me say like this: FA is a machine, and the task is addition operation. Now, can FA do the addition operation or not? Okay, so this is the question. This is the very basic question which we are going to answer in this subject, and that is nothing but computational capability of machine. Okay, and the very first is how machine perform computation. So how actually FA do computation, how PDA do computation, and so on. We will study all these things in pretty much detail in this subject. Okay, so I hope I have cleared all the basic concepts. Okay, so what exactly we are going to study in this subject? That is the two basic things. The very first is how machine perform computation, and second is, given a machine and a task, whether the machine is capable of doing this task or not. That is nothing but computational capability of machine. Okay, so we will study these two things in pretty much detail in this subject. Okay, so let me move to next slide now. Okay, so before going to before we dive deep into this subject, we will study basic history of this subject. That is how this subject was evolved. Okay, so you all must be wondering that this is boring thing and so on, but no, it's very, very interesting. Just bear with me. Within 2 to 3 minutes you will feel lots and lot of interest in this subject. Okay, so basic history will motivate you to study this subject. Okay, so it will create lots and lots of interest in you. Okay, so how this subject was started, or you can say history of this subject. Okay, till early 90s. Okay, till early 19th century. 19th century. Till early 19th century, everyone believed that logic is complete. Logic is complete. Everybody believed that logic is complete. So what is the basic meaning of complete here? Complete means it can prove anything. Okay, so first of all, let me tell you about the basic thing, that why we are studying logic. Okay, you all by now, I think you all have studied the logic subject. That is the basic fundamental of discrete mathematics also. So in discrete mathematics, we all first study this subject logic. And why we study this subject? Because it is used to prove some set of statements. So given a statement, we know that it is true, then we can prove that statement with the help of logic that it is true. Okay, and given a statement is false, so I give you some statement and I say that this statement is true. Now next question I will say that can you prove that it is true? So to prove that the statement is true, you will take the help of logic. Okay, so till 19th century everyone believed that logic is complete, that is we can prove given a statement. Okay, given a statement, we have a statement, given a statement, we can easily prove with the help of logic that it is true, and we can also prove with the help of logic that the given statement is false. Okay, given any statement, we can prove that it is true or false with the help of logic. This is the basic fund. This is the basic, you can say, crux of what I'm going to say right now. Okay, so statement, given any statement, easily we can prove that it is true or false with the help of logic. Now next question is, given any statement, can I give any statement and you know that it is true or you know that it is false? Now still, can you prove with the help of logic that it is true or false? Yes, you will say that obviously sir, we can obviously prove it because we already know that it is true. So by hook or by crook, by something, by doing some step-by-step procedure, we can prove it is true, or we can prove that it is false. But no, we cannot do it. Okay, so till early 19th century everybody believed that yes, this is true, that given any statement, we know that it is true or we know that it is false, and still we can prove that with the help of logic that it is true or false. Okay, but in mid 19th century there were some scientists, the name were say Alan Turing. Okay, so let me use a different slide. Okay, so first of all you should copy these few words. Okay, and then I will move to next slide, and in next slide I will give you some basic information, or let me throw some light on this basic fact that how with the help of logic we can prove some statement is true or false. Say, let us suppose I say all birds fly. Okay, and I think you have already studied this logic subject in computer science and in aptitude also. So we try to prove, we have some argument and we try to prove that the given argument is valid or not, and so on. Like this, say we say that all birds fly. So we can, so first step is, if you have an English statement, then we will try to convert it into logic statement. Say we say that for all x, bx implies fx. Okay, so this is the logic statement for all birds fly. So for all x means every object in this universe, if that x is a bird, then it will fly. Bx means x is a bird, fx means it will fly. Okay, so every object in this universe, if x is a bird, then it will fly. Like this we convert this English statement into logic statement. Now, okay, now listen carefully. Obviously we can convert any English statement to logic statement, but when we got this logic statement, how we will prove that this statement is true or false? So here the simple logic will be, for all object in this universe, okay, if you want to prove it false, you have to show me a bird which does not fly. Then I will say that obviously this statement is false. And to prove that this statement is true, you have to pick each and every bird in this universe and you have to show that it fly. Okay, so like this we can roughly, I'm saying roughly, that we can prove this statement is true or false. Now given any statement, now let me say it again, given any statement, you already know that the statement is true or you already know that the statement is false, but still with the help of logic we cannot prove that the statement is true or false. With the help of logic means step-by-step procedure. So like this, say we have a statements, we have some group of statements, and we will like this is one statement, and like this we can have many statements, and we will convert them into logic, and we will apply some logic rules of inference, and we try to prove that the given argument is true or false and so on. Like this, we try to prove with the help of logic the given statement is true or false. Okay, don't worry if you do not know all these things, don't worry, we will study all these things in pretty much detail in discrete mathematics subject. Okay, so we have some statements, okay, and we try to convert them into logic, and by some rules of inferences we conclude that the given argument is valid or not. This is the rough idea. Okay, so in simple wording I can also say like this. So let me use next slide. Okay, so logic means nothing but step by step. Okay, step by step you try to prove something. Step by step try to prove something. Try to prove something. Okay, like you do in mathematics also, we try to prove some theorems. So how we exactly prove theorems? Say we say that A is equal to B and B is equal to C, so final conclusion is A is equal to C, like this. So this is an example of, you can say this is the simplest example of logical statements. Okay, so we say that A is equal to B, B is equal to C, so final conclusion is A is equal to C, and so on. Okay, so in mathematics also, and in lots and lots of areas of many subjects, we use logic to prove something. So simply I can say that logic, the basic, you can say aim of logic is to prove something, that it is true or false. Okay, so now let me come to our basic scenario, what I was trying to say you. Okay, so just note it down fastly. Now let me say you like this. Till early 1900, yeah, you can say till early 19th century, till early 19th century, everybody believed that logic is complete, and everybody believed that given any statement, we know that it is true, then we can easily prove that it is true, and given any statement which is false, we can easily prove that it is false. But there were some scientists, say their name was Alan Turing, Gödel, and so on. There were many scientists, and I have just say a few names, and rather I have said only two names, that is Alan Turing, Gödel. They believed that logic is incomplete. Logic is incomplete. Okay, so they were having some intuition kind of thing that logic is not complete. We cannot prove everything with the help of logic. But you know, intuition is nothing. See, intuition is you can say actually entire humanity. So entire human civilization, you can say their brain, or you can say their right brain. The right brain, entire right brain is intuition. So we cannot say that intuition is nothing. But according to mathematics, we can say that intuition is not enough to prove that something is true or something is false. You have to properly prove it. Okay, so Alan Turing, Gödel, and so on, these scientists were saying that we have some intuition that logic is incomplete. But nobody believed, because intuition is nothing. They said intuition is nothing. We want a proper proof, that how you can say that logic is incomplete. Proof in the sense, you give some example, you give something, you give some statement, and you try to prove that this statement is true or false, and you know that this statement is true or false, but you try to prove that with the help of logic we cannot prove this statement is true or false. Okay, so this is a very, very important statement. I have said very deeply, so try to understand it properly. These scientists tried to prove that logic is incomplete with the help of logic itself. This statement is very big, and it was next to impossible at that time. Why it was impossible? Because with the help of logic itself, you want to prove that logic is incomplete. Why I am saying with the help of logic you want to prove? Because the only tool to prove anything that is true or false is logic only. Without logic, we cannot prove anything. So now, with the help of logic, You want to prove that logic is incomplete. That is, with the help of logic, you want to prove that the given statement is true, but still you cannot prove the given statement is true. Okay, so I know that uh, you might be facing some confusions and all these things, but still you do not worry about all these things. I will keep I will say each and everything is in proper detail when we'll jump to this subject. Okay, so you just try to listen all these things just like a story itself, because we are just studying the history of the subject only. Okay, so Alan Turing and Gödel, they said by intuition we think that logic is incomplete. So every scientist said intuition is nothing. But I have already said intuition is a very, you can say, a very prominent part of humanity and entire right brains. Our brain is divided into two parts: left brain and right brain. Left brain is logical. Okay, logical, L for logical, L for left. And the right brain is intuitive. Okay, so logic means P implies Q, Q implies R, P implies R, and so on. Everything whatever thing logical. Okay, whatever is logical, that is your left brain. Logical means true or false. Okay, maybe, can be, cannot be, these are not logical statements. Okay, so for example, you all are engineers. Let me give you a real life example. Say, I think she loves me, I think she do not loves me, and so on. So these things. So the question thing, she loves me or not, the question, the answer may be may or maybe. Okay, may or may not, and so on. So this is not a logical statement. Okay, so logic means strict yes or no, nothing more than that. That is 0 or 1. Okay, logic means true or false, 0 or 1, nothing more than that. 0 means you can say false, and 1 means it is true. So maybe, may not be, these are not logical statements. Okay, maybe, may not be, these are not logical statements. So left brain is logical, that is complete true, false, and so on. And right brain is intuitive, which which led you thinking about what exactly this may be, and so on, all these things. Okay, so intuition is but exact idea of until now, nobody nobody knows what exactly is intuition. Okay, nobody has idea about it. The moment we understand this intuition properly, then we can build computers which have intuition. Till now, computers have only logic and no intuition. But when intuition will be understood properly, then computer will have logic as well as intuition both, and then computer will be like just like human beings. Till now, computer is not like human being because they have logical brain. They do not have any intuition. Okay, so they cannot think properly. Okay, so they can just do logical things. That's it. Okay, so see, the story is very, very big. So I do not want to waste your time in all these things, but just I am giving you idea of all these things. Okay, so please note it down all these things, and let me move to next slide. Okay, okay, so in mid 1950s, yeah, in mid 19th century, Alan Turing and Gödel, they properly proved all these things. Okay, so whatever I was saying, that they were having intuition, but every scientist say that properly prove all these things, and it was next to impossible. But these scientists properly proved in mid 19th century that logic is incomplete. They properly proved it. Okay, so in mid 19th century, these scientists properly proved that logic is incomplete. Logic is incomplete. They properly proved all these things. Okay, of course, we do not need to go to all these details that how they exactly proved and so on, but it was next to impossible at that time. And then after mid 19th century, foundation of TOC was laid down. TOC subject started. Okay, so about Alan Turing, a very interesting fact about Alan Turing. Biggest award which is given to any computer scientist is Turing Award. Okay, so computer scientists do not get Nobel Prize and so on. Nobel Prize is given to core subjects like science, physics, chemistry, mathematics, and so on, and literature also. But the highest award which is given to any computer scientist is Turing Award, and it's just because of this scientist Alan Turing. Okay, he made a machine called Turing machine, and with the help of that machine, he proved that logic is incomplete. We will study all these interesting things in pretty much detail in this subject. Okay, so we will study about Turing machine and other machines also in this subject. Okay, so in mid 19th century, TOC foundation was laid down and this subject was started. Okay, so because they proved that logic is incomplete, that means we cannot prove something. That means we cannot prove everything with the help of logic. So next very important you can say thought which will come to our mind is, say, let me use next slide. See, can we have some problem? Can we have a problem which cannot be solved, which can't be solved? Or you can say a problem, we know that problem has solution. We know that problem has solution, but still it cannot be solved. Yes, they proved all these facts. Say, in the first go, you will be thinking that this is meaningless thing. See, problem, we know that it has a solution, that obviously we can solve it. Solve means we can reach the solution step by step. Solve means what? Reach the solution step by step. Reach solution step by step. Okay, so solution means reach solution step by step. Okay, so but no, okay, we cannot reach the solution step by step with the help of logic. Okay, so this is a very vague, you can say very vague point, that we have a problem and we know that it has a solution, but still we cannot solve it. Okay, so Alan Turing, Gödel, and so on, these scientists properly proved these things. Okay, so from this concept, a very important concept came, and that concept was problem of undecidability. That is, we have some undecidable problems. We have some undecidable problems. Okay, so roughly I can say, let me use different slide. Roughly I can say problems are of two types. Problems are of two types. First is decidable problems. Decidable problems. And the second is undecidable problems. Undecidable problems. Okay, so decidable problems are those problems for which we have algorithm. Okay, we have algorithm to solve them, like given number is prime or not, find a prime number greater than the given prime number, and so on. There are a given graph is Hamiltonian or not, and a given graph is Euler or not, and lots of problems you have already studied in data structures and algorithms also. Okay, so all these problems are decidable problems. That is, we have algorithm to solve them. Undecidable problem means what? Listen carefully. No one in this world, say, roughly I can say that they do not have algorithm. Okay, so let me say like this also. Undecidable means what? Obviously they do not have algorithm. Now let me give you a very powerful statement. The powerful statement is, no one in this world will ever be able to write algorithm for these problems. Right? Algo for these problems. So there are some problems. Okay, so how this concept of decidability and undecidability came into the picture? This came into the picture just because Alan Turing, let me move to previous slide. Alan Turing and some other scientists, they together proved that logic is incomplete. That is, we cannot prove everything with the help of logic. Hence, this concept that we cannot prove everything with the help of logic, this concept laid the foundation that there are some problems which have solution, but still we cannot solve them. Okay, so then the concept of decidability and undecidability came into the picture. That is, there are some problems for which no one in this world, this is very big statement, and I'm not saying from the air, I'm not saying this statement from the air. Actually, this has been proved properly that no one in this world will ever be able to write algorithm for these problems. No one will be able to write. This has been proved formally, or you can say mathematically. Okay, so there are some problems. Okay, so next question which will come to our mind is, okay, next question. Note it down fastly. Okay, let me use different slide. Next question which will come to our mind is, say we may think that decidable problems, we have studied lots and lots of decidable problems, and undecidability we haven't studied till now and we haven't heard till now. So our brain will think, or you may think, that undecidable problems will be very less. Few tens or thousands or hundreds of problems will be there which are undecidable, and rest all are decidable problems. So decidable problems are infinite and undecidable problems are finite, and they are very less in numbers. But actually the picture is completely different. Okay, so let me show you something. Undecidable problems are much larger than decidable problems. Okay, this is fact. Just you can think like this. This is a sea and this is water. Okay, sea is filled with water. These are all undecidable problems, and you take a bucket of water from this sea, and that is decidable problems. You can think like this. So decidable problems are just a bucket filled with water, and undecidable problems are entire sea. So sometimes rather there are some situations where some scientists give very wrong predictions, and this was one of the wrong predictions, and everybody believed that logic is complete, so every problem is decidable, there is nothing called undecidable and so on. But in mid 19th century, when Alan Turing and Gödel, they proved all these things, and then the picture was completely changed. That undecidable problems, there are lots and lots of undecidable problems. In fact, entire sea filled with water is just like undecidable problems, and only a bucket filled with water is decidable. Okay, so entire picture was changed. I hope you are feeling lots and lots of interest in this subject by now. Just because I am showing you a complete different picture, a complete different scenario of logic, science, and all these things. Okay, so let me say you this thing also. Logic is nothing but your science. So science is not complete till now. You think that every problem can be solved with the help of science. No, science is not complete till now, because science is still logic only. When science will cross logic and it will touch the intuition part, then everything will be completed. But the only problem is intuition is not properly understood till now. Okay, when intuition will be properly understood, then AI, ML, all these fields, artificial intelligence, machine learning, I think you know all these terms. So this there will be a huge, or you can say humongous, research will happen in these areas, and entire computer science scenario will be changed. You all must be thinking that computer science is over. uh, Lots and lots of research has already done and so on, but I will say that computer science is barely begun till now. Okay, just because intuition has not been understood till now. Once the intuition will be understood, then entire scenario will be changed. AI ML will progress just like anything. Exponential growth in research and so on will happen, and everything will just like human. Okay, okay. So finally, you have understood that decidable problems are very less, but undecidable problems are very, very high. There are lots and lots of undecidable problems, but decidable problems are very, very less. Okay, and let me give you one more interesting fact. Okay, let me use another slide for this thing. See, sometimes scientists give very, very wrong predictions. No? Sometimes scientists give very wrong predictions. And this was one of the wrong predictions, that logic is complete, but scenario was completely different. Decidable problems are very, very less, and undecidable problems are very, very high. Okay, and another one scientist I want to mention here itself, just to give you some idea that scientists also, they are also wrong sometimes. Say you have heard about Thomas J. Watson. Thomas J. Watson. He was a very, 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 very brilliant scientist, and in fact, in till now, IBM labs, top-notch research is done in IBM labs, and these labs are named after this scientist. This is Watson Labs. Okay, and till now, lots and lots of cutting-edge research is being done in Watson Labs, and this scientist gave a very vague statement, and that was only 5 computers in this world. If you install only 5 computers in this world, then all the problems can be solved. All the problems can be solved. Okay, okay, so see now, all some scientists give very, very wrong statements. Okay, but still science is science only, na? So still lots and lots of research is going on and all these things, but I just want to say that some scientists give very, very wrong predictions. Okay, and they are you can say their research area, and they are very brilliant, but still they give very, very wrong statements. Okay, and this was one of the wrong statement which was given by Thomas J. Watson. And you know why he said this statement? He said this statement by arguing that we do not need any operating system in the computers, because only 5 computers in this world will solve all the problems. So we can have computer operators, and they can operate it very well. So we do not need any operating system, and we do not need to automate the linking, loading, all these steps of the computers. Okay, so without operating system, still we can run computer can run properly, but for each and every problem we have to write algorithm, or you can say we have to write a problem. Sorry, we have to write program for that. Like if you want to create a file, then you have to make a program which will allocate space in the hard disk. Okay, so our life will be very, very tough. But this person argue that we do not need operating system. We need just one operator for one computer, or you can say some set of say some few operators which can manage one computer, and only 5 computers in this world will solve all the problems. Okay, but the statement is in today's world, this statement is absolutely meaningless. Okay, so let me give you some more idea. Okay, let me use next slide. See, the fact that why I am saying undecidable problems are just like a sea, and decidable problem are just like a bucket. Okay, why I'm saying this? Let me give you, yeah, let me throw some light on this fact also. See, undecidable problems, the set of all undecidable problems, or you can say undecidable problems, uh, undecidable problems are uncountably infinite. Okay, and the decidable problems decidable problems are countably infinite. Okay, so I think you know what is countably infinite and what is uncountably infinite. If you do not know all these things, then don't worry, we will study all these things in pretty much detail in this subject itself. Countable, roughly you can say countably infinite is a small infinity and uncountably infinite is a big infinity. Roughly, like you can say countably infinite is the set of natural numbers, and uncountably infinite is the set of real numbers. Real numbers is uncountably infinite, but natural numbers is countably infinite. See, between 1 and 2 there are infinite real numbers. Okay, so real number set is very huge, or you can say very big. It's much bigger than your natural numbers set. Okay, and countably infinite just mean that we can identify this is your first number, this is your second number, this is your third number, and so on. One is your first number in natural number, two is the second number, three is the third number, dot 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 dot, like this. But real number is uncountably infinite. This means that you cannot identify this is my first number, this is my second number, and so on. Forget about everything. Just tell me what is the first real number. You will say 0.01, or you can say positive, first positive real number. You will say 0.01. I will say no, it's 0.0001. You will say no, it's 0.00000001, and so on. So the fact is that we do not even know what is the first real number. Okay, so first, second, third, and so on, we cannot identify them properly. Okay, so next I can say, building this idea, I can say real numbers is just like a water. Okay, you cannot say this is my first, this is my second, and so on, but your set of natural numbers is just like this. Okay, these are discrete numbers. Discrete in the sense there is a sufficient gap between the numbers. This is your first number, this is second number, and so on. You can say like this, but in water you cannot say this is my first drop, this is my second drop, and so on. Okay, so you cannot say like this. Okay, so this is your just this is your set of real numbers, and this is your set of natural numbers. So natural number set is discrete and the real number set is continuous. Okay, so obviously I can say that the real number set is much bigger than your natural number set. Okay, real number set is much more bigger than your natural number set. Okay, so real number is uncountably infinite. This is rough idea, and natural numbers is countably infinite. Okay, so with the help of logic, say let me use next slide. Okay, let me use next slide. So if a set is countably infinite, then this set will be discrete. So you can imagine that we have a table, and on the table we have some apples. Okay, and logic is just like a fork, 0 1. Okay, so these are the two branches of fork, and one is 0 and one is 1. Okay, and between 0 and 1 there is nothing. So let me say like this, between 0 and 1 there is nothing. So there is a sufficient gap between the numbers. That's why I'm saying it as a discrete set. Discrete, why I'm calling it as discrete? Because there is sufficient gap between the numbers. Okay, but there is almost negligible gap between the numbers. We cannot differentiate between them. Okay, so imagine like we have two dots, and these are so closely placed to each other that we cannot differentiate between them. This is just like a real number, but natural number, these two dots have sufficient gap. There is no problem at all. 1 and 2, these two numbers are different. Okay, there is sufficient gap between them. Okay, so like here also I am saying 0 and 1, just like a fork. Okay, so this is your logic. So with the help of fork, you can easily pick these apples. You can easily pick them. Okay, but what if I say on my table I have poured some water? Now with the help of fork, can you pick this water? No, not at all. That's why logic cannot, you can say logic is incomplete and logic cannot solve each and every problem. Okay, so the decidable problems, the set of all decidable problems is just like your apples, that is discrete set. Decidable is discrete. Okay, but undecidable problems is just like water. Undecidable problems is just like a water. So you, with the help of fork, you cannot pick the water, but you can pick the apples. Okay, so imagine this, these are just like apples and this is just like water. With the help of fork, you put some with the help of fork, obviously you can put these you can pick these apples, but with the help of fork you cannot pick this water. Okay, so this is the basic fact, that undecidable problems are you can say uncountably infinite, but decidable problems are countably infinite. And because these are countably infinite, so logic can pick them, and because these are uncountably infinite, logic cannot pick them. Okay, logic cannot pick them means what? Logic cannot differentiate between the problem. You can say that the problems are so closely placed with each other, p1, p2, p3 and so on, these are so closely placed that logic cannot identify the differences between these problems. Okay, so logic will think all these problems are same, but actually these are different. I hope I am able to give you some intuitive idea about what exactly we are going to study. Don't worry if you are thinking that this subject is difficult. I will make it very, very easy for you, and I'm just giving you an idea, an intuitive idea of all these basic concepts. Okay, and that's it. Okay, and I have used said something about, I want to say something about Godel also, and then I will complete this lecture. Okay, so you know, natural numbers, set of natural numbers, then set of whole numbers, and a whole number has just one extra zero, and a natural number is 1 to infinity and whole number is from 0 to infinity. And then we have integers. Okay, and then we have rational numbers. Okay, and then we have real numbers. Okay, and then complex numbers and so on. So let me take till this step only. Okay, so till rational numbers. Okay, let me use different color. Till rational numbers, that is till q, all these are countably infinite. But after that, this is just like water. That is irrational numbers. Irrational number, you know, na, rational numbers plus rational numbers union irrational numbers. Rational union irrational numbers. This is your real numbers. So rational union irrational is real numbers. So rational numbers is countably infinite and irrational numbers is uncountably infinite. And with these two sets union, we get real number that is also uncountably infinite. So irrational numbers set is uncountably infinite. So I can say like this. So till rational number, these are just like apples. Okay, these are just like apples, and after that it's just like water. Okay, so roughly you can imagine in TOC also. Okay, I do not want to use technical words in this lecture, but still in TOC also we will study like this also. Okay, so till we have languages like regular languages and a CFL, CSL and so on. So dot roughly I will say till RE languages, that is recursive enumerable languages, everything is countably infinite. Okay, countably infinite. And after that we have non-RE languages, that is uncountably infinite. Roughly I'm making the diagram. Okay, that is uncountably infinite, just like water. So are you able to establish a kind of relationship between these two sets? Yes, they are just similar. No? These are similar. Say till something we have countably infinite, and after that uncountably infinite. Similarly, TOC also, till RE languages everything is countably infinite, and after that it is uncountably infinite. Okay, so it's not accident. It's just because of Gödel's incompleteness theorem. Okay, so we will study, don't worry about all these things, we will study all these things in pretty much detail. I am just giving you idea. Okay, so this is just because of Gödel's incompleteness theorem. Gödel's incompleteness theorem. Okay, and this theorem simply says that any axiomatic system is incomplete. It has he has given two theorems, and one of the theorem is any axiomatic system is incomplete. System is incomplete. Roughly I can say that this theorem is saying that whatever topic you are studying, like probability, in probability you say that probability of sample space is 1, but if you are in the system of probability itself, you cannot prove that probability of sample space is 1. Of course you will say, sir, what are you saying? We can obviously prove probability is ratio of two things, that is favorable outcome or total number of outcomes. So sample space is nothing but your entire set, no? All the possible outcomes. So obviously it will be 1 and so on. Yeah, you can prove it, but it has certain assumptions which are known as axioms. Okay, or say you can say in Euclidean system, you will say parallel lines will never meet. Okay, so why they are not meeting? Or you can say they will meet at infinity. So will they will meet at infinity or not? We do not know. We cannot go till infinity now. Okay, so there are some axioms, or you can say there are some statements which are so basic in the system that we cannot prove them that they are true or false while we are in the system itself. So if you want to prove these statements, then you have to go outside the system. Only then you can prove that these statements are true or false. Okay, so I think you might be facing very difficult, you might be facing some difficulty in understanding this theorem. I know this theorem is a little bit difficult. I will properly say it, and with formal statements and all these things, I will properly prove it also. Okay, so the basic thing is, Gödel's incompleteness theorem is saying any axiomatic system is incomplete. Okay? You say whatever axiomatic system, that will be incomplete. TOC is also an axiomatic system, because we will say that the machine will accept the string or reject the string. So you cannot say that it may or may not be accepted and so on. So why we cannot say like this? Okay, so why we are saying that machine will only accept or reject and so on, and nothing more than that? That means may or may not and so on. Why these things are not coming? Okay? So don't worry, how we will study all these things. Okay, so these are some assumptions. This is an assumption that machine will only accept or reject. We cannot say, we cannot lie in between. That is, we cannot say that machine may or may not accept and so on. So this is an assumption. So whatever system, so any system which is having some assumptions, that system is incomplete. Okay, this is called incomplete theorem, and this is very, very beautiful theorem. Don't worry, we will study all these things in pretty much detail when we will dive deep into this subject. Okay, when we will dive deep into the subject, we will study all these things in pretty much detail. Okay, okay, so that's it. So let me give you brief idea about what exactly we are going to study in this subject. Okay, so we will study 3 chapters. Okay, we will have 3 chapters. So the first chapter is finite automata and regular languages. Second chapter is PDA and CFLs, and the third chapter is Turing machines and decidability. Okay, so more than 50% of TOC will be covered in the first chapter itself, and it is the most important chapter, and it's easy also. Okay, and the PDA and CFL, you can think about it as approximately 20%, and Turing machines and decidability is approximately 30% of the syllabus. And obviously weightage is also just like this also. Okay, so if you are expecting 10 marks from TOC, then 5 marks from first chapter. Okay, so first chapter is very, very important. And in the next lecture, we will study about what exactly we will study in the first chapter, and some basic you can say terms and basic formulas which we are going to study in this subject. Okay, we will, in the next class itself, we will first study few basic terms. Okay, we will study few terms like string, language, and so on. And after studying these terms, when we will be comfortable, then we will jump to our first chapter, that is finite automata and regular languages, and I will properly discuss the syllabus of this chapter, and we will jump to the respective topics. Okay, thank you so much. Bye bye.